One, two, okay. Do you want to make this announcement? Okay, I think. Okay, hello. Welcome to Module 2. Okay, couple of announcements. We'll have a mid-semester survey. Is it out? It's out on Piazza already, and we'd appreciate it will be up on till Monday. And so we'd appreciate if you fill it up. If you fill it out, if you get more than 75% plus participation, everyone gets an extra point on the midterm. So, and remember, grading is absolute, so this is your point. So work collaboratively to get that one extra point. Another important thing for people this is the first midterm at Berkeley, please don't arrive later than 8:30. Okay, we're not going to admit anyone after 8:30 p.m. So you have like half an hour, a buffer to forget that midterm's going on, and then remember and come to the midterm. Okay? Thank you. So let's talk a little bit about what Module 2 is all about. This is not really a circuits module, right? Like how people normally call it. This is essentially a way of thinking how to build systems. Systems that interact with the real world, systems that acquire the information from the real world, do some processing on that information, and then do something. And so in the Module 1, you already started learning kind of the basic fundamental techniques of how to do some mathematical processing, some manipulation. In Module 3, you'll learn some pretty cool algorithms that will connect you immediately to some very nice applications of what you will be able to do if you are able to acquire signals from the outside environment. In Module 2, we'll figure out how to connect the two, right? How to connect the outside environment to an information that it offers to some tangible information that we can process, right, and act upon. So let's try to figure out a few sensor components that you may know that are, or have them in your pockets that are very popular. Sensors are things that turn some analog world information into something that a circuit or a building block in a processing unit can process, right? So anyone has any ideas about sensor? Yes? Gyroscope is a sensor. That's right. So what does it sense?
The orientation of the device.
Okay, gyroscope senses the orientation of the device. Where do you have a gyroscope?
In the phone?
Yeah, in the phone, or in many other pieces of hardware, but most popularly in the phone, right? That's how your phone knows that you've turned it around, and it adjusts the screen, right? And in fact, it does the screen adjustment through a matrix projection of the image, which, if you look at last semester's midterm, for example, there was an example like that. Any other sensor? Yes?
Quadrature
Quadrature
encoder.
encoder. Can you elaborate a little bit on that? Okay, the text rotations where? Oh, okay, yes. That's a good example. Something more massively widespread. Yes. Which one? Oh, okay, buttons, home button on your phone. That's a great example. Nowadays, it does the fingerprint, right? So it has to actually sense the shape of your skin on the finger, right? So that it's able to detect that, the fingerprint, and then log you in your phone, right? Anything else kind of close to that? Yes? Camera, a great one. Okay, so why is camera so great? Any thoughts? Everyone loves, yes? Okay, so it used to be an analog device turned into digital. What is that? What does analog mean? What does digital mean? Analog is kind of continuous values, like it's kind of calculus type math, right? Digital is kind of like linear algebra, right? And so with digital, you can potentially get higher fidelity and expose yourself to all the computational power that is now in our processors, digital signal blocks, right? But more than that, if you look at the recent explosion of AI, for example, do you know where the origins of that are? Anyone? AI is only 6 years old. It's a toddler. And not a toddler, but like a kindergarten style type. So how do people know where it all began? Yes?
I believe it began primarily when trying to get a computer to be able to recognize subsets of images.
Yes, and I stand corrected. AI in its current incarnation or attempt is only 6 years old. There are previous versions of AI that are about 26, 30 years old that kind of died out, and this latest generation is only 6 years old, and it is because it basically came about. There's this competition in recognizing features from images, and in 2012, computational power was big enough that a neural network was able to go and train on that image database, which is called ImageNet, and get smart enough to recognize images better than the hand-coded code done by programmers. Okay, so that was a revolution. But it came about because of two things. One thing was the abundance of images that people collected, and that's because of the cheap camera sensors that everybody had on their phone and could just upload the tagged images. Second was the GPUs, graphics processing units, were fast enough now to be able to crunch the training algorithms for hours and hours. At that point, it was a few days to train the network, but still. And since then, they've continued to improve. So it's all because of these hardware systems, sensing and processing, that we see more rapid continuation of scaling of machine learning. I read recently a fascinating fact that the computational demand, because of AI, doubles every 3.5 months. If you remember the graph I showed you at the beginning of the class, which was the Moore's law, which is how the hardware was developing, it was actually doubling every 2 years. So that was our previous rate of hardware development. Doubling the capacity every 2 years. AI and machine learning demands, let's round it up to 4 months. Doubling every 4 months. And if you do a little bit of calculation 10 years out, and you will see how much more accelerated the demand is. And it has to come from somewhere, from some hardware advancements, better understanding of us how to build systems. So in Module 2, we're going to start doing that and showing you some of the basics and how to do these things, and then continuing into 16B, 151, 61C, a great class to do that. Okay, so what we're really talking about here is having some analog world here, and there's some information that we're trying to sense. Right? And the role of the sensor is going to be to convert that information, which could be light, like in our in images. It could be mechanical, a vibration, like we talked in the gyros. It could be anything else that we, let's say, humidity or temperature, all sorts of different things. And we need to convert it into some quantities that hardware understands. Right? So anyone has any idea what quantities, what physical quantities does hardware understand? Circuits, yes. Yes, that's right. So these are electrical quantities. So voltage. What else? Yes. Current. Yep. Okay. So let's stick with these two. Then this goes into some processing unit. So this is still information, but it's just moved from one domain into another domain, from mechanical, temperature, humidity, pressure, whatever, into this electrical domain. It's represented either as a voltage or current or both. Then the circuits can do some processing on it. So sensor will have some circuits. Processing will have some circuits. Sensor will have something else that's essentially called a transducer. It takes whatever physical variable is and moves it into the electrical domain. So we'll say transducer. Right, a circuit. And then now we have information. Today, this information is going to be digital at this point, when we're feeding the processing unit, but definitely out of the processing unit. And then we have actuation, or some action, right? And you mentioned the quadrature decoders. Well, that rotation, detecting that, will cause some control system to do some steering control, for example, in an automated driving car. Or automated driving car has cameras, and LiDAR, which is another type of sensor that senses the depth. That goes into neural networks, for example, that do feature extraction of the images to figure out, is the car in front of you or around you? Is a pothole? Should you avoid it? Where do you sit with respect to the lanes on the street, etc., etc. Many different neural networks working to figure that out, and then create a decision, and that decision then needs to steer the wheel. So the actuation is actually the act of steering the wheel or hitting the brakes or the gas pedal, etc., etc., right? And then again, that actuation either hits the virtual or real world. Like real world would be like in an automated car. Virtual would be you push the button or the touch screen on your phone. That's another sensor. And the phone did something internal to the phone, right? Displayed a web page. Things like that. So these are all essentially similar principles. And once you understand these conversions and how to build these, how the information flows, how to move it from one electrical variable to another, you'll be able to build very complex systems. Okay. Today we're going to, yes?
What's the definition of information in terms of changing this like physical dimension and then it uses this physical dimension as the actual processing? So how do you define information?
This is really an excellent question, and maybe Gireeja can do it better than I can. But you know, to me, information is an understanding of something, right? Or an understanding about some event that I'm interested in. In fact, that's maybe even a better definition, because sometimes I'm only interested in some piece of information. There's a lot of excitation in the world around you, right? But you're interested in a particular form of that excitation, and that's information to you. Everything else is either interference or noise, right? And so let's say that's information, right? Based on that particular excitation from the analog world, you want to create some action, right? And you're definitely right. That excitation comes as any other physical variable. You need to convert it into currents and voltages to be able to later do something with it, right? Okay. So today we're going to learn the algorithm for circuit analysis. And the reason why I say algorithm is literally computers do that today, right? So nominally, you don't really need to know how to do this, except that once you figure out how to do this, you'll be freed to do synthesis. Right? So computers today can only do analysis. You give them a node netlist, it's a graph, just like the pumps stuff that we talked about earlier. They look at this netlist and they go zzz, and they give you an answer. And that answer is exactly the kind of math as we'll see that you did in Module 1. It's basically matrix inversions, linear, nominally linear systems of equations. If they're nonlinear, you linearize them, but pretty much all the same deal. Okay? What computers cannot do is do the following. Build me a circuit that has this much gain, this much frequency range, and senses the input with this much sensitivity. The computer goes, what? Right? The smartest computer in the world cannot do that. Okay? The reason that's synthesis. That is, from a problem specification, you try to figure out what are the circuit topologies that can do these types of things. Not to mention more complex things, like I want to sense something that's pressure, turn it into current, and then do something on it. The computer cannot do that. Right? So we will do this actually in this class, because we're going to teach you how to synthesize, how to design to specification. A lot of homework problems will be about that, as well as the exam problems. But because that's what modern engineers do. They build stuff according to some specifications or something they've dreamed up. Computers help them analyze that stuff once it's built to make sure that that stuff is rock solid. Does it make sense? Okay, so let's first see what computers do. It's kind of a necessary thing. So this will be electrical circuit analysis algorithm. And so it's really a tool. And in fact, if you walk into Corey and you look on the right side, as you walk into Corey between the two doors, you'll see a little plaque on the wall from IEEE that awards Berkeley a recognition for building a tool that's called SPICE. Okay? This computer tool was done in the 80s and really helped people solve for currents and voltages in really large, complex integrated circuits. Once people started building integrated circuits and started having thousands of components, it was really hard to do these matrix inversions by hand, very tedious. And so people automated this whole process, and Berkeley researchers were the first ones that did that and open sourced this for people to use. And the whole Silicon Valley is half based essentially on this type of tool and circuit design that helped basically build everything. So that's where we got the recognition. Okay, so let's see what happens there. First thing that we have is quantities. And I'm going to do this really from the perspective of the computer. The computer knows nothing about an electron, knows nothing about any physical meaning of any of these components. And so we're going to just treat it exactly like that. So forget your high school physics just for a moment. It will come handy when we start doing the design. But for analysis, it's absolutely not needed. And in fact, I would caution you to really not try to apply your intuition when you're doing circuit analysis. Because often you kind of remember wrong, or you're trying something, and you can often make a mistake. It will force you to skip a couple steps, and then you will be kind of in an uncharted water and not know what to do. So You can try that, but if you're unsure about what to do, just fall back to this algorithm and it will always produce a solution, right? Then you just turn your brain off and just go and write it out. So that's what we're going to do in this lecture. Just turn our brains off for the physics intuition and just do the math, okay? So I'm just going to define these quantities as like quantities that a computer understands and operates on. So we're going to have quantities, an analytical symbol, and then we're going to have units. Okay, so first quantity we said, was voltage. We're going to label it as V. Okay, and units will be volts. V. For Alessandro Volta, is one of the early inventors in circuits, electricity, things like that. In fact, NVIDIA names all their GPUs based on scientists, right? So Volta is one of them. Current is another. We're going to label it as I in our circuits. It's amperes, short for that is amp. One important thing is that units are really handy, okay? You don't need to know their physical meaning, but when you go and you do a lot of number crunching, in the end of the day, if you're calculating current, it should not come out as ohms or as volts, right? And if that happens, then somewhere in your calculation you didn't do something right. So that's what a first indicator that something's wrong. So always do a unit check in the very end or throughout your calculation if you're kind of unsure what's going on. That will tell you what's going on. So resistance is another one. Ohms. This is omega. My poor rendering of Greek alphabet. Okay. So resistance at this point is just a quantity. If you want the physical intuition, it's essentially exactly like the word says. It's opposition to movement, right? I'm able to walk because there's resistance between my soles of my shoes and the floor, right? So this is the same thing. When charges run through the wires, they encounter resistance or opposition. There's atoms all over in that wire. They're hitting them, etc. But you don't really need to know that for this type of analysis. We'll just use it as a quantity. Now, there's a circuit diagram. So this is kind of very similar to what we did pumps. We just drew some circles and some arrows. That was a diagram of something. It was a model of something. So circuit diagram is again, just a model representation of what's actually going on and something that a computer understands. Like it can basically parse it and extract some mathematical formulation from it. And so we're just going to say this is a collection elements where each element has some voltage across it and some current through it. So we're just going to draw here an element. So this is an element, it's just a box. And there will be current, I element, and some voltage, V element, across it. Now, the way I drew this, notice there's a plus and a minus for V element. Right? Well, that just means that I've measured this voltage between these 2 points, a plus and a minus point. Right? And voltage is this relative quantity. It only applies to things. It's only a relative thing between a certain point in the circuit and another point in the circuit. There's another quantity related to voltage that we're going to touch on soon that's called potential. And any point in the circuit has some potential. And then voltages are just differences of these potentials. Right? So it's important to keep track of where your reference is when you're taking that difference. Are you doing A minus B or B minus A in terms of potentials? Right? And that's something that's going to be kind of important as we move forward. By the way, all of this stuff is essentially in Note 11 on the website. So you can kind of check it in more details over there. Okay? So, see if we see it well. Okay. So, since we mentioned these elements, they're now just boxes to us. Let's define some of the key elements as building blocks and what are their properties, and then we can go and analyze or put together some circuits. So, key circuit. If you think in computer jargon, I'm now defining certain classes and functions or methods within the classes to say what does that object class do, right? So the first one is a wire. A wire, the way we're going to use it is kind of an ideal wire. It's just a connector between 2 points, okay? So I'm going to draw it just like this. And this wire, I'll label just like any element. We'll have I element and V element. Right. And as for each one of these elements that we have, we will represent its behavior as some relationship between the voltage and current of that element. Right? That's called the IV relationship. So, can anyone guess what is the voltage on this element? 0. Okay? So there is a physical explanation why that's the case, but here we will just define it like that. We're just defining it for the computer. Computer has no idea about any of the physics. For the computer, you define that voltage across this element is equal to 0. Right? And it's happy. Okay? And then the current is what? Any ideas? Yes? Okay, yes. So the response was, it's actually set by the circuit outside of this element. Right? In other words, it can be whatever. The current through this element can be whatever. The voltage will still be 0. But the actual value of the current is set by whatever is the circuit that this wire is connected to. Right? So this is set by the circuit, by the external circuit. Right? Okay. So what we do here, for every element, we'll draw a little graph that is essentially I element and V element. Right. And so on this graph, how does the line look like? The relationship. How can I represent the relationship between voltage and current? Anyone in the back? Yes? On which axis? Okay, on the I element axis, that's right. So it's this line. Okay? because V element equals 0, current can be anything. So that's really our y-axis. Okay, so let's do second element, resistor. Okay. Now my artistic skills. Okay, so this is going to be R, I element, and again, plus minus V element. Okay, so again, I'll define, well, in this case, let's just look at V element. What is V element? Okay. Anyone else? I know you know. Yes. R times I. Yeah. So it's R times I element. How's anyone knows what this expression is? Yes. Ohm's law. Okay. So this is just, again, an interesting piece of information, really not necessary for the computer to do anything. Computer just sees this definition, V element equals R times I element, and that's a linear relationship, right? That we can, again, represent on this IV. Okay, what's the shape here? Anyone in the back? What's the shape of this relationship? How do they represent it on the graph? Yes? Okay, great. So it is a line through the origin with a slope of 1 over r. Right? And so now you can see something actually pretty interesting is that what happens if that r goes to 0? Yes? Yeah, it just does this, right? So the line essentially becomes y-axis. So that kind of tells you that if I asked you a question, what's the resistance of this wire that I defined, you should be able to answer, right? Based on these equations. Nothing else. Don't use your physics intuition, nothing, right? Okay, so element number 3. Open circuit. Okay? So we're going to define an open circuit like this. Okay? So here, in the definition of the open circuit is that I element equals 0. Meaning there's no current through open circuit. That's just by definition, like that. We mark that by drawing it as this gap, meaning like there's no flow that can go through it, but it's just a symbol, right? It just says there's no current through this element. Okay, what is the voltage? What's the voltage on this element that cannot carry any current? 0? It's not 0. It's also set by the external circuit. Now, I'm asking you these trick questions. You really should say, what? Why are you asking me this? This is undefined. Syntax error. The reason is that we're just defining the behavior. This can be like some totally alternate universe, right? Where physics is totally different. We're just defining some behavior. So for this element, we're saying, okay, if you say open circuit, I don't know what the voltage is. It's whatever else sets it, but I know that current is 0, right? So this is set by external circuit. And we can again draw this I element, V element. And what is this going to look like as a function? Yes? Yep. So it's going to look like the line along the x-axis where I element is 0 and voltage is whatever. Okay, so now, let's just move it up a little bit. I'm going to do the fourth element. Now we're getting some action, because so far we only defined components that kind of don't do really anything. They're just in the way. But the thing that does stuff is the battery. Right? Once you put the battery to the circuit, it wakes up and starts doing stuff. And so voltage source is one element like that. So we're going to define it as a plus and a minus. Label it as Vs. This is kind of the internal polarity of the battery, right, of the source. But how I label I element and V element is a totally different thing. Remember, I can draw the element as a box, right? I can draw a box around each one of these elements that I've drawn and just label I element and V element on that box. So that labeling is totally different from what's actually inside the box. So let's say in this box, there's Vs, right? And I can even draw a dotted line for a box, right? And now I'm going to say, okay, in this box I have I element, and I'm measuring a voltage V element. It just so happens that these two pluses coincide, but they don't have to. As we'll see later, it can be different, right? So, but as I've defined it here, V element is going to be Vs. And I element is going to be anything. Again, set by the outside circuit. This means this voltage source is so powerful it can handle any current while it's putting out this voltage Vs. Right? So again, this is set by external circuit. Okay, and the relationship for IV is what? What's the shape of the curve? Okay, it's a vertical line at where? Okay, great. So it's a vertical line at voltage equal to Vs. So this intercept point is Vs. That's right. Okay. So let's define one more. 1, 2, 3. Okay, so we're going to define element number 5, which is current source. Again, this is kind of an internal flow of current in that source, Is. And then I'm going to define I element and V element. And in this case, I element will be equal to Is because these two arrows match. If I defined I element in the opposite direction, then I'd write I element equals minus Is. Right? So V element here, again, is something. It's, again, set by external circuit. Okay, let's draw a diagram. In this case, where's the line? Yeah, okay, good. So it's Is. Right. Okay, one of the key things in all that we've done so far is that V element and I element can be positive or negative. I cannot stress this enough, okay? V element and I element are just some mathematical quantities. They can be positive or negative. Don't be freaked out when you do the circuit analysis and your current to that element that you've defined turns out to be negative or voltage is negative. That's completely okay because as you'll see later in the algorithm, we're defining these completely arbitrarily, okay? And your solution may be different than your friend's solution with regards to how you label these elements, okay? So that's nothing to worry about. Just be careful not to try to apply some sort of a circuit intuition there, and then you kind of get confused. So just crank it out, okay? So let's do some rules for circuit analysis. Okay. These rules are kind of like operators. If I get a diagram, what applies, right? So the first one, we're going to call for short KVL. It's actually Kirchhoff's voltage law. So, and it says that the sum of voltages across the elements in a loop equals 0. Okay? Let me give you an example. So let's say we're going to draw a source and then a wire and a resistor. Right? Let's say in this case, how many elements do we have in this circuit? Yeah, like a computer looks at this, tries to parse the graph. How many elements? 4, right? What are these 4 elements? Source, resistance, and 2 wires, right? And these things here are called junctions. That's basically how you connect the 2 elements together. And there are going to be some special properties about that. But let's now go and just label the element voltages completely arbitrarily. I'm not doing anything special here. So I'm going to say just, okay, let's say this is V element 1. Let's say this is V element 2. This is V element 3. And let's say this is V element 4. Right? What KVL says is that V element 1, so I can pick a loop, let's say going from this point around, and so I get V element 1 up minus V element 2, because I'm going down, minus V element 3 minus V element 4 equals to 0, because I'm now back at this point. Right? Is that clear? Any questions here? Yes? Oh, why are some positive and some negative? Well, look at how I'm going in this loop. I go here from minus to plus, right? So I'm kind of going up. And then I go from plus to minus. So I'm going now down this voltage element 2. And then again down voltage element 3 and down voltage element 4. So if I draw this, if I take this circuit and I kind of stretch it as a graph, I can sort of do it like this. So this is V element 1. So I go from a minus to a plus, from here to here. And then I go V element 2 plus minus V element 3 plus minus V element 4. Right? So I go all the way up, and then I start coming down. This is the same thing like you go to Tahoe, You climb the fast chair all the way up to the top of Heavenly, and then you start coming down different trails, but these different lifts actually can still connect you to the top, but through smaller altitudes, right? So this is exactly the same thing. This is an alternate path to the top through these few smaller potential differences, right? Does that make sense? Okay. So method number 2 will be KCL, Kirchhoff's current law. And this is actually the one we're going to use much more. And is kind of, should be very familiar too, but let me just frame it. And so then you'll go, oh, okay. The current flowing into any junction must equal the current flowing out. Right? So junctions in the circuits, we just define them. Any current going into the junction, or the total sum of currents going into the junction, has to be equal the sum of currents going out. Do we see this before anywhere? Yeah. Yeah, the flows problems, right? The pumps. That's basically what's going on. What comes in has to come out, right? Okay. So let's do an example. So let's say this is I source. Again, 4 elements in the circuit, right? So I'm just going to go and arbitrarily define the currents. Can you see that? Yes. Okay. So say this is I element 1. This is I element 2. This is I element 3. This is I element 4. Okay? So let's say I pick this first junction. What can I say about I element 1 and I element 2 if I apply this law? Yeah, they should be equal. I'm just going to write I element 1 equals I element 2. I could also write this out as I element 2 minus I element 1 equals 0. Then kind of becomes more mathematical in a sense that I get some zeros on one side and I get some linear combinations of things on the other side, and you can start saying, oh, I'll define as a plus anything that goes out of the junction, as a minus anything that goes into the junction. I can start formulating some things, and we'll see that very shortly. But let's just go around. So for this junction, again, we have I EL2 equals I EL element 3. For this junction, I have I element 3 equals I element 4. And then for this junction, I have I element 4 equals I element 1. Now, if I look at these 4 equations, is there any redundancy there? By redundancy, I mean, like, for example, linear dependence. Yes? Okay, yeah, I can do mathematical manipulations on first 3 to get the 4th equation, right? So, I don't really need it. We're all about efficiency. So, we only want to specify as many equations that are needed to actually solve something. This one doesn't help us, right? So, when we do circuit analysis in later steps, we will keep this fact in mind, that we don't have to look at all the junctions in the circuit, but we can look at all but one. Okay. So let me just squeeze in real here a few other things. For example, if I wanted in my labeling for some reason I went in and I labeled I element 2 prime, like this, and not in that other direction. How would the equation look like for this junction? I'd have I element 1 plus I element 2 prime equal to 0, right? Because both of these are flowing into the node, right? And nothing's coming out. So the sum of currents that flow into the node have to be equal to the sum of currents flowing out. Right? Nothing changes in this circuit. I just had assumed a different flow of current. That's fine. I'll just get, if I'm wrong, I'll just get a negative value. That's fine when I solve it, right? So, but no biggie, no big deal. Real quick example 2 would be if I have a junction like this. So I do I element 5, I element 6, I element 7, right? So for that one, I'll just write, again, the same thing. I element 5 plus I element 6 equals I element 7. Does that make sense? Yeah, these are just rules. Okay. So one more that's kind of related to that, and just to make sure people are not confused, there's KCL within the element. Okay. So let's say we said the element is just a box, right? So I can define I element like this, and I have plus minus V element. Or I can also write it as this. Sorry. Right, so I've just moved the arrow, right? This is the same exact thing. In fact, I element is also here. Right? Meaning same current that goes into the element comes out of the element. How do I know that? Which rule applies within the element? Anyone? We only learned 2 rules. So you have 50% chance of hitting it. KCL, right? At any point along the element, there is some junction of some materials or something, right? So for every piece there, the same KCL applies, right? So don't assume that some current goes into the element, but an explosion of current comes out of the element, right? Or like 10 times that current. No, same current flows through every element. Okay, now you may have noticed something really subtle that I did as I was kind of drawing all these elements, right? There's something I didn't tell you, but I was doing it constantly. Anyone guessed what that is? How I was labeling the elements. Yes? Okay, that's related. So you mean, like one side, let's say I kept V element always at the top, right? But what did I do also? Yes? That's right. So I always assumed that the current of I element flows into the plus terminal. And that's actually on purpose. So that thing is called passive sign convention. Okay? So I element goes into a plus terminal or out of a minus terminal. Right? Meaning this is legal And this is also legal. Right? Only these two combinations are legal. Everything else is not. And we'll see later when we talk about power and power dissipation and things like that, why this definition makes sense. But for now, again, we described it to a computer. It says, yes, sir, that's how it's done. That's it, right? Don't worry about it. Okay, but keep in mind that you don't make a mistake. You don't apply passive sign convention on some components, and you don't apply it to other components, because then things will go bad. Okay, so finally, the algorithm. Okay, so circuit analysis algorithm. Before we do it, I just want to clarify a few things so that it's actually clear what's going on. So, first, that voltage equals a difference of two potentials. Okay? The purpose of the algorithm is to find currents through elements and potentials of inputs or outputs of each element. And we called those junctions. Right? So let's see how that looks like on a circuit. So this is the same circuit we looked before. Okay. R plus minus. So 2 wires, source, and a resistor. Right? So I'm going to go now and explicitly label the potentials on each of the junctions. So this is the junction. I have a potential U1, U2, U3, U4. Right? So U1 and U2 are potentials. There's just some quantities. So U1, U2 are potentials. Right? V1 is U1 minus U2, and I'm going to do that by first marking what V1 is. So for V1, the plus is here, the minus is here. Right? Or, okay, to not confuse you, let's do the minus like this. So V1, the plus sign reference of V1 is at U1, the negative is at U2. That's why I can write V1 as a difference of these two potentials, U1 minus U2. And this is voltage. Right. And if V1 is my element voltage, how does I1, which is the element current, have to look like? In which direction does it flow? From U1 to U2 or from U2 to U1? Plus is here. So by passive sign convention, how does it go? 1 to 2, right? So I1 would have to go this way. Right? So I1 will be current. Okay. And I can then say that for this element, V1 equals 0. This is the element wire element definition. This is not something that the circuit tells me. I know this. When I see this element, I know that this is true. Right? That will tell me now something about the circuit. Because if V1 equals 0, I know from this definition of voltage that U1 minus U2 is equal to 0, right? And that basically means that U1 equals U2. Well, I just solved for the relationship of U1 and U2 in this circuit. Does that make sense? So I'm just applying the definitions, which is definition of a wire, definition of what voltage means, and I come up with a relationship between those two potentials in the circuit. Okay. Now, this is actually pretty interesting. Means if my quest is to solve for potentials in the circuit, right, that was the algorithm, then if I have a wire in the circuit, it's kind of really extra work for nothing to solve for the potentials at its two ends, because I always know they're the same, just from the definitions of things, nothing to do with the circuit. So if that's really true, and I'm really lazy, I don't want to go and explode my space of the circuit solve by treating wires as kind of decent elements, right? Wires are just solved by definitions, nothing had to do with the circuit. So, in other words, I can redraw this circuit kind of looks the same, but I'm not going to say this is a separate junction from this one, because I know their potentials are the same. I'm going to call this whole thing here a node. Okay? It's just a node. It's a node with same potential. It's a part of the circuit that has exactly the same potential, and I'm interested in finding out what that potential is. So, then, I'll just say that, let's say in this case, this node has some potential UA, and then, again, here, there's a node that has some potential UB. Oops, yes. Right? So now, how many unknown potentials I have in this circuit? I have 4 junctions, I have 2 nodes. How many potentials are unknown? 2, right? That's right. UA and UB. And so that just eliminated 2 variables from my linear system of equations that I have to solve, right? Plus all the currents through the wires. I don't even care about that, right? Because I really care about the currents through these other elements. Okay, so the point here is that we can collapse junctions with same potential into a node. And once I do that, I'm simplifying the problem, right? In the note 11, you will see it starts by all 4 junctions, does the full solve like we will do, and then it's a bigger system of equations. I'm not that good at math, so I'll do this and have a smaller system of equations to solve, right? Okay, so let's do that. Now we come to the kind of algorithmic point. So, like in any algorithm, it's all about steps. It's a step-by-step procedure. So let's just outline it. Step 1, pick a reference node and label it as a 0 potential. So then all voltages measured relative to this node. So what that means, kind of graphically, is this. We'll pick, let's say, the bottom node, and we'll label it 0. Now, this is similar. You'll see in some circuits, people go and add something like this, right? they call that ground. I'll try to not use that symbol because many people get confused thinking there's some current flowing into that little stem. It's really not. It's just a label, right? It's just a label saying, hey, that node in the circuit is my reference node. I'm going to look at all of these. It's like the surface of the ocean, right? That's basically your elevation reference point. It could be the bottom of the ocean, but we just picked the surface, right? And that's basically the same thing. We just picked a node in the circuit and say, I'm going to measure all the potentials where they are relative to this. So all the voltage differences are with respect to that node, right? So that's all that there's in step one. Just pick something. You will pick this node. Your friend will pick the top node. That's okay. Perfectly fine. You will get slightly different values when you calculate things, but that's okay, because it's all with respect to that node. Okay, step two. Label all remaining nodes as potentials, UI. And let's say there will be U1 through UN minus 1, right? If you have n nodes in the circuit, you'll label n minus 1 of them. Right, so again, here, it's a simple one. So we have just one. We've labeled this as 0. We'll label this as U1. Right? And just so you see how convenient this is, if I was looking at a voltage between this node and this node, that will be U1 minus 0. Well, that's actually the same as that potential value. That's just because I defined some node as 0. Right. So this is voltage between node 1 and node 0. Step 3. Label all branch currents with IM. Let's say I1 through IK. Arbitrarily pick directions of IM. So no overthinking this, right? We have a 0 here. We have U1 here. I'll just arbitrarily pick the directions. Let's say I1 is the element and I2 is the element. I could pick the other orientation of the arrows as well. Yes? Oh, sorry. See now? Okay. Okay, step 4. Okay? Now we add the voltage, the element voltages. Just to each element, following the yes. The question is it okay if I1 is going up out of the positive of Vs? Think about it this way. I can box Vs in a little wooden box with 2 wires sticking out, and you wouldn't know where the plus inside Vs is. So for that element, I'm free to label the current anyway I want, right? Because this is just an element current that I defined, right? That's a great question. And so, but now in this step 4, I have to relate the element voltage to the element current using which convention? Something we talked about 10 minutes ago. Passive sign convention, right? So this is, again, related to your question, independent of what is in the element. In the element. So a little drawing here. Plus minus VSR. U1 is here. 0 is here. I defined I1 this way. I defined I2 this way. Now, because I defined these element currents like this, I need to obey now the passive sign convention, which means here, on this R element, where's the plus? If I want to label V1, where is the plus? Here or here? Up, right? So this is, V2. So for V1, where is the plus? Here or here? Top or bottom? Bottom. Yeah. This is usually where I get a question. No questions? It's clear? That's great. Right? We're just applying the convention, right? We said earlier that, this is okay. That's exactly what it is, right? So I just turned it upside down. Plus, minus, current's going up. That's exactly this situation here. Okay. Almost done. So, step 5. Now, we formulate AX equals B. Right? Where X is going to be a vector of our unknowns. We got I1 through IK and U1 through UN minus 1. Right? Okay. Step 6. Let's start filling the matrix. Right? So we're going to first use KCL to fill as many rows of A as possible. What does that mean? As possible. How many rows of A can I fill? At each node, I can apply KCL. Should I apply to all the nodes? No? How many nodes? I have n nodes. How many nodes should I use? Yes? n minus 1. So I want to keep linear independence, right? So number of nodes minus 1. So it's n minus 1. Right? So let's do that. Plus minus Vs. I have R. I have I2. Plus minus V2, U1, 0, I1, plus minus V1, right? And so from here, if I apply KCL to the top node, I only need to apply to one node because I have two nodes in the circuit, right? So I'm going to apply, usually we apply it to all the nodes that are not a reference node, but it doesn't really matter. So let's say to the top node, I can write I1, which is what comes in, is equal to I2, which is what comes out, right? I can also write it as I1 minus I2 equals 0, right? Or the other way around. And so I can now form the matrix okay? As what? I read these coefficients. So this is I1, I2, and then I have U1 here. So what should the row look like? Yes? 1, negative 1, 0. And then here, 0, right? Okay, this should remind you of some matrix that you did earlier. Anyone? This piece? Okay, I'll let you think a little bit about that. Okay, so step 7. Use current voltage relationships for each element to fill the rest of the A matrix. The A matrix dimension is number of nodes minus 1 plus number of branches where the elements are, right? So I just got n minus 1 here, and now I'm filling for all the element branches, right? So okay, let's do that. Plus minus Vs R I2 plus minus V2 U1 0 plus minus V1, and I have I1. So for voltage source, what do I have? So that's this one. Okay, let's call this V element 1, just so it's clearer. V element 1 is what? Has to do something with Vs, right? It's measuring the same thing that this source is doing. So just applying the definition, what's going to be V element 1. Anyone? Yes? Vs, okay. Does everyone agree with that? Negative Vs, I'm hearing. Why do you think it's negative Vs? Yeah, we flipped. You see, it was the definition said if this plus coincides with this, then V element is Vs. If not, it's the opposite, right? So it's actually minus Vs. You're right. Okay, but then also V element 1 tells me what's the voltage difference between this node and this node. Right? On this end where it's minus, it's U1. On this end where it's plus, it's 0. So V element 1 equals 0 minus U1. Right? So it's minus U1. Well, that just tells me that minus U1 equals minus Vs, so U1 equals Vs. Okay, that's one piece of information. For the resistor, what do you get? So let's call this element 2. So I get that V element 2 equals, it's just a definition, right? It's I2 times R. I2 is the element current times R. V element 2 is also U1 minus 0. That's just a voltage definition across, right? So that's U1. Okay, now from these two, I can write that U1 equals I2R, or let's say I2R minus U1 equals 0. Okay, so let's just write the matrix. We have 1, minus 1, 0. I1, I2, U1 equals. So we go but from this one, 0, 0, 1 equals Vs. Right, so that's this one. And then we're writing I2R minus U1. So we get 0, R minus 1 and that equals to 0. Voila. This is our system of equations. Now, if you just manipulate the rows, you should see it's already diagonal, triangular, upper triangular, so you're kind of done almost, but I'll let you finish it. When you do, you'll get this. U1 is Vs, I1 is Vs over R, and I2 is also Vs over R. And now we've solved for all the variables in our circuit. Does that make sense? If you're confused about this junction versus node, there is node 11 goes to kind of the junction one where it keeps all the wires, and we'll also repeat this in discussions, so you'll get it completely. Okay? Thank you.